Welcome to Calculus, a new approach using simple school algebra. And thank you for your interest in this presentation. My name is Michael Range, and I am a retired mathematics professor from the State University of New York at Albany. During my professional life, I mainly did research in the area of multidimensional complex analysis. I published a number of research papers and also a book which has become a very popular introduction to this field. In case you want to find out more about my professional background, please just go ahead and Google my name, R. Michael Range, and you will find lots of information. So in recent years, however, I have been involved in calculus. I'm looking for a new approach that makes life much easier for our students. And this is what this presentation is about. So the first part deals really with the basics, double points and tangents for polynomial curves. So let us get started then. Have you ever wondered why calculus is so complicated and difficult? For example, why do we need to begin by learning the new sophisticated concept of limit and the intriguing real numbers, that is, involving infinite decimal expansions, even when we look at the most simple examples? Concretely, let us look at the slope of the tangent to the graph of f of x equals x squared at the point 2, 4. Now, the standard approach considers the limit of the following expression, which once you introduce the expression for the function into this, you get 2 plus h squared minus 4 divided by h, where you take the limit as h goes to 0. And of course, we assume that h is different from 0. Now, intuitively, this leads to the expression 0 over 0, which is, of course, meaningless. And this shows that limits can indeed be quite complicated. However, in this case, simple algebra leads to calculating this expression and simplifying it. At the end, you get 4 plus h times h divided by h, where if h is different from 0, you can cancel the common factor in h in numerator and denominator. So the final answer then results in the somewhat complicated limit expression that we had looked at the beginning into simply limit of 4 plus h as h goes to 0. Everyone will now agree that the obvious answer should be that this limit is equal to 4. Unfortunately, the instructor will usually say, hey, not so fast. We cannot just ignore the limit concept and set h equals 0 in an expression that was derived assuming that h is different from 0. And so we are forced to begin with a detailed discussion of this new and quite complicated concept of limit in order to justify what appears so obvious. And that's the way it has been for almost 200 years. But isn't it natural to ask whether there's not a simpler approach to solve what looks like a very simple problem? As I will show you in this presentation, the answer is indeed yes. Thank goodness. Moreover, the simple method can easily be adapted to handle all algebraic functions, such as polynomials, rational functions, roots, and more. Furthermore, all the standard rules of differential calculus can be introduced and practiced in this elementary setting. And it all can be done within the familiar rational numbers. No need to complicate matters with real numbers at this point. Finally, when one tries a simple method with non-algebraic functions, such as the fundamental exponential function, one quickly recognizes its limitations. Consequently, more sophisticated new tools and concepts need to be introduced. So you will understand at that point why concepts such as limits and the intriguing real numbers must be introduced. And I hope that this will help you as you learn about the new ideas that lead to the heart of analysis. In order to understand the central new idea of the simple algebraic method, it is best to begin by reviewing the notion of a tangent. We all have learned about tangents to circles. Here's a picture, and recall that the tangent to the circle at the point P is that line which is perpendicular to the normal at P. It is that line which connects the center to the point P, and the line perpendicular to it is a tangent. The idea of a tangent is indeed quite old. Over 2,000 years ago, Greek philosophers and geometers studied tangents to various curves, such as circles, parabolas, ellipses, and more. For them, a tangent to a curve at a point P on the curve is a line that touches the curve but does not cut it. Certainly, this language is somewhat vague, but it seems to fit what we have seen with a tangent to a circle. Now, let us look at some other simple examples to help us to identify the key features more precisely. So we consider two graphs of f of x equals x minus b squared plus c, where b and c are some fixed numbers. The curve on the right, which is this one here, corresponds to the case where c is negative. So the first part here is always greater than or equal to 0, but with c being negative, some of the things will turn out to be below the x-axis that is negative. Now, the x-axis intersects the graph of f in two distinct points, and surely it would be appropriate to say that the axis cuts the curve in each of these 2 points. The curve on the left corresponds to the case where c is equal to 0. In this case, the points of intersection have blended together, one on top of the other, right here. If you pull this down a little bit, the 2 points will separate. But at this place, the 2 points coincide. We just see 1 point. And certainly it would seem appropriate to say that the x-axis touches the graph of the curve at that point, but certainly does not cut it. So according to Greek geometers, the x-axis surely is a tangent to the curve at that point. And algebraically, in this case, the touching point b, 0 is determined by the solutions of the equation x minus b squared is equal to 0, which is a quadratic equation for which the 2 roots coincide. That is, we have a double root, or 0, or a root of multiplicity 2. Geometrically, this touching point is a double point. That is, 2 points that just happen to lie on top of each other. So only 1 point is visible. Of course, as we pointed out a short moment ago, if the curve is just moved down a little bit, the 2 points of intersection separate and both become visible. So by just looking at this most simple example, we conclude that the ancient notion of a touching line is made precise geometrically by recognizing that the special point where the line touches the curve is really a double point. And furthermore, that this is made precise algebraically by saying that the relevant equation that determines the points of intersection has a double 0. To be precise, there are special situations where the touching point covers not just 2 points, but 3 or even more points. The corresponding relevant algebraic equation then has a 0 of multiplicity 3 or higher. For example, consider the graph of y equals x cubed at the point 0, 0, so right around this point. The x-axis sort of touches and cuts the curve in a special way. The curve meets both sides of the axis. It's sort of a touching cut. Notice that if the x-axis is just rotated slightly counterclockwise, so we get this kind of position, the point P that we have when the axis is just horizontal suddenly splits up into 3 distinct points where the line intersects the curve, 1, 2, and 3. So initially, P covers 3 points, and we may call it a triple point, and this property still qualifies the x-axis as a tangent to the curve at P. And algebraically, the points of intersection of the x-axis and the graph of y equals x cubed are the solutions of the equation x cubed equals 0, which indeed has a 0 at x equals 0 of multiplicity 3. As we shall see, this simple idea to identify tangents can be implemented very easily as soon as one learns about the quadratic equation and the special case of double roots. We illustrate this by considering the case of a tangent at the arbitrary point P equals a, comma, f of a on the graph of the parabola f of x equals x squared. Now we consider a line through this point P, and it's defined in point-slope form by the formula y is equal to f at the point A plus m times x minus a, where m is a slope. When x is equal to a, then of course the value of y is just f of a, which is a squared. So this is the equation of the line. That's why it's a point-slope form. Its points of intersection with a graph of f are the solution of the equation f of x equals the equation of the line. This is a quadratic equation, which can be written in the form x squared minus a squared minus m times x minus a is equal to 0. Now, instead of using the familiar formula for solving quadratic equations, we just use a standard factorization. X squared minus a squared is equal to x plus a times x minus a. And the equation can then be written as x plus a minus m times x minus a. We can have the factor x minus a as a common factor of x squared minus a squared, and then of m times x minus a. This shows that the roots are a, which is of course no surprise because we constructed the line to go through the point a squared, and the other 0 occurs when x is equal to m minus a. So the line will intersect the graph of f in a double point. That is, the above equation has a double root at x equals a, precisely when m minus a equals a. And that means that m has to be equal to 2a. We have thus found the slope of the tangent at this particular point by a completely elementary method. No limits and no mysterious quotients, 0 over 0. And for example, the tangent through the graph of f of x equals x squared at the point minus 3, 9 has slope 2 times minus 3, which is minus 6. And hence, the equation of that tangent line is equal to y equals 9 minus 6, which is a slope, times x plus 3, which is just the point-slope form of that line. So let me point out about the history, a brief comment, that the identification of tangents by looking for double zeros of the relevant equation is actually much older than the familiar standard identification via limits. It goes back to René Descartes, 1596 to 1650. He was one of the main philosophers and mathematicians of that period. And this was over 50 years before Newton and Leibniz introduced the ideas that eventually developed into the standard introduction to derivatives. Unfortunately, Descartes and his followers ran into major algebraic complications as soon as they considered curves more general than ellipses or parabolas, and this algebraic method was eventually forgotten. However, as you look at the method we just presented, it looks so simple. And as we shall see, it works for general algebraic functions with minimal complications. So one may well wonder why philosophers and scientists in the 17th century overlooked this simple method. One possible explanation is that the point-slope form of lines, something that every high school student today knows, was not known or used at that time. In fact, this point-slope form appeared explicitly in the literature only about 100 years later. Perhaps we can say that philosophers and scientists, they were just so under the spell of Euclid, who had introduced the axiom that a line is defined by two different points, that they had a difficult time accepting the idea of introducing a line just in terms of one point and its slope. Anyway, we shall now apply this method that was so easy and successful in the simple case of f of x equals x squared to an arbitrary polynomial p of degree n, given by the following expression, where the numbers a sub n up to a sub 0 are fixed numbers, the so-called coefficients of the polynomial. And recall that p has degree n if the leading coefficient of the highest degree term is non-zero, so that this really occurs in the expression. And polynomials of degree 0, they're just going to have a constant term like this, and of course it has to be non-zero. What we want to do is find that line through the arbitrary point a, comma, p of a on the graph of p that intersects the graph at that point in at least a double point. As before, this means that the relevant equation for the points of intersection has a 0 at x equals a of multiplicity 2 or higher. Now, the equation of a line through this point a, p of a, is given by y is equal to p of a plus m times x minus a, where m is its slope. Again, we're using the point slope form to describe this line. The relevant equation for the points of intersection then is p of x is equal to p of a plus m times x minus a, which we can rearrange as p of x minus p of a minus m times x minus a equals 0. So this is a polynomial equation of degree n, and it's hopeless to try to find the solutions. But just in the case that we considered earlier, we don't have to look for all solutions. We're just interested in the point x equals a, which is the obvious solution, and we want to determine when that is a 0 of multiplicity bigger than 1. So recall that in the simple case, y equals x squared, we had seen that the factorization of x squared minus a squared is a critical ingredient. So in the case at hand, we thus look for a similar factorization of p of x minus p of a. And fortunately, there is a general result that readily gives us what we need as follows. A theorem. If the polynomial p of degree n greater than or equal to 1 has a 0 at the point x equals a, that is, if p of a is equal to 0, then p has a factor, x minus a. That is, there exists a unique polynomial q of a of degree n minus 1, so that p of x can be written as a product of q of sub a, that polynomial of degree n minus 1, multiplied with x minus 1. Now, this result is, in fact, one of the most basic results about polynomials that should be well known. but we shall review its simple proof a little bit later. And in the case at hand, we shall apply this theorem to the polynomial p of x minus p of a, which does indeed have a zero at x equals a. When you plug in x equals a here, you have p of a minus p of a, which obviously is zero. So we can apply this factorization result. P of x minus p of a is therefore the product of this polynomial q of x of degree minus n minus 1 multiplied with x minus a. By using this result, we can therefore rewrite our equation in the form qx times x minus a minus m times x minus a. We can factor out the common factor x minus a, and we're left with the first factor q at x minus m multiplied with x minus a. So clearly this equation has a zero of multiplicity 2 or higher, precisely if the factor q of x minus m also has a zero at x equals a. And this occurs exactly if the slope m equals the value of q at the point a. Therefore, the line through a, p of a, will be a tangent precisely if its slope m equals q of a. Let us formalize our result in the following theorem that completely solves the tangent problem for any polynomial. So the theorem just repeats what we just did. So excuse me for repeating, but it's such an important result. So let's take a polynomial p of degree n greater than or equal to 2. Otherwise, we would just have a line. And let a p of a be a point on its graph. Then there exists a unique line through a p of a that intersects a graph at that point with multiplicity greater than 1. The slope m of that line is given by q at a, where q is a polynomial of degree n minus 1 in the factorization p of x minus p of a equals q of x times x minus a. And of course, we call this unique line given by the theorem the tangent to the graph of p at this particular point. And its slope m equals q of a is called the derivative of p at that point. And it is denoted by d for derivative at p of p at the point a, or also simply by p prime at a, which is a standard notation that has been used for a long time. Note that this process of finding the derivative of the polynomial p defines a new function whose value at the point x is a derivative of p at the point x. And we shall see shortly that the derivative is also a polynomial. We shall now prove the factorization theorem that is a critical ingredient in the theorem we just proved. Let us first consider the special case that p has a zero at a equals 0. Since p at 0 is just the constant term a sub 0, the constant term in the expression that defines p, it follows that we must have a sub 0 is equal to 0, assuming that p has a 0 at 0. So you write out the polynomial p of x. There is no constant term at the end. Every term in here has a factor x, so of course you can factor it out. And you get this factorization. The beginning part here is a polynomial of degree n minus 1, and this obviously proves the theorem in this case. Now, for the general case, now we assume that p has a 0 at the arbitrary point a, and we introduce a different kind of polynomial defined by p star at the point x equals to the original polynomial that we're considering at x plus a. When you take p star at 0, that is p at 0 plus a, so that's just p at the point a, which is 0 by the assumption. So the case we just considered, we just proved, gives us that p star at x is equal to a polynomial of degree n minus 1, let us call it q star, at x times x, where this is the polynomial of degree n minus 1. Now we want to get back to p, but note that that's very easy. P star evaluated at x minus a, that's the same as p evaluated at x minus a plus a, so the a cancels here, and you just get back p of x. So therefore, the original polynomial p of x can be described in terms of p star as p star at x minus a, and we look at this factorization, we get q star at x minus a times x minus a. And this proves a theorem, since this term here is certainly, after some algebra, a polynomial of x, q of a, which has degree n minus 1. Now, just a quick word about the uniqueness of the factor q sub a, is we also have a factorization p of x equals q1 times x minus a. Then subtracting this from the first factorization, one obtains, well, 0, that's p of x minus p of x. And, you get the difference q sub x, q sub a times at x minus q sub 1 at x multiplied with x minus a. Well, when x is different from a, then this part here has to be 0. So this polynomial here has to be 0 for all x different from a, which shows that this is a 0 polynomial, so q sub a is equal to q sub 1. Now, how about evaluation of the derivative of a polynomial? Well, in principle, the critical factor can be calculated explicitly by using what is known as a division algorithm for polynomials. And that's something analogous to the division process for integers. But this is much too cumbersome. It is much easier to simply look at each summand in p of x separately as follows. The typical summand is of the form f sub k of x is equal to a constant times x to the power k. So let us find the derivative of f sub k at the arbitrary point a, c times a to the power k on its graph. As we just saw in the general case, the critical ingredient is the factorization of f sub k of x minus f sub k at a, and q sub k, in this case, is the polynomial of degree k minus 1. And it is very easy to verify that this particular polynomial is given by this expression here. You can check it out easily. This generalizes what we have in case k is equal to 2, because then this is just x times 1, and this is 1 times a. So x plus a, which is what we had before. So consequently, q sub x is equal to a. Q sub x at a equals this constant c times k times a k minus 1, which is what you get here when you evaluate this, so that the derivative of f sub k at the point a is equal to this constant c times k times a to the power k minus 1. Now, this differentiation rule that we just established here, that the derivative of x to the power n is equal to n times x to the n minus 1, that is known as the power rule. Now, to handle the case of a general polynomial, we use the following elementary lemma. Suppose that f and g are two polynomials, and then the derivative of f plus g or f minus g at a is equal to the derivative of f at a plus or minus the derivative of g at a. So in words, the derivative of the sum or difference is the sum or difference of the derivatives. What else would we expect? The proof is pretty obvious. Let's fix the point A and consider the two factorizations. And the respective polynomial factors are q sub f and q sub g. Let us just use a case, the plus case addition. Then f plus g at x minus f plus g at a, that is, of course, f at x plus g at x minus f at a plus g at a, and you can rearrange this. You have f sub x minus f sub a plus g sub g at x times g at a, and the first part is q sub f at x multiplied with x minus a, and the second part plus g of x minus g of a, we can replace this with the factorization q sub g at x times x minus a. So clearly, q sub f plus q sub g is the appropriate polynomial in the factorization of f plus g at x minus f plus g at a, and therefore the derivative of f plus g at a is the value of this polynomial at a, which is, of course, the value of the sum of the polynomials, and therefore we get simply the sum of the derivatives of f, respectively, g at the point a. So just as easily, one can verify that the derivative of c times f at the point a is simply this constant c times the derivative of f at a for any constant c. So these results now readily imply the following results for any polynomial of degree n, namely the derivative of p at a, you apply derivative to each summand by the rules that we just introduced, that you just verified. This gives us a sub n, the constant, comes out as a factor, then n times a to the power n minus 1. The next term gives us a to the n minus 1 times n minus 1 times a to the n minus 2, and so on. And replacing the arbitrary point a by the variable x, we see that the derivative of p at x is simply this expression here, which is clearly a polynomial of degree n minus 1. So just to give a quick example, if you take p of x is equal to this particular polynomial, then the derivative is equal to 3 times 4 times x to the power 3, minus 5 times the derivative here by the power rule of 3 times x to the squared, 4 times 2x, and here 6 times the derivative of x, which is just 1, and the derivative of the constant term is 0. So it's that easy. So this completes our discussion of the tangents to the graphs of polynomials. And note again that we have only used the familiar rational numbers and simple algebra, nothing more complicated like real numbers and limits. This approach could be introduced to students as soon as they have learned the basics of the quadratic equation, including the special case of a double root. One only needs to extend these basic concepts to the case of polynomials. In part 2 of this presentation, we shall verify all the standard rules of differentiation in the context of rational functions, that is, quotients of polynomials. So this concludes our first part of this presentation. Thank you again for your attention.